Does an inverter generator guarantee your equipment won't be exposed to dirty power? When purchasing a generator of a given capacity, the inverter generator often costs maybe 3 or 4 times the cost of the old synchronous generator. And one of the reasons you might spend that kind of money is that the waveform does appear to be very beautiful on the scope, but one of the things to think about, it's not only the output of the generator, but the waveform can be disturbed by the loads that are on this generator. Our homes are filled with all kinds of electronic devices, such as microwaves and dimmers and switching power supplies, fluorescent ballasts, all kinds of things which can produce a distortion in waveform. And you know, the list just goes on nowadays. In this video, I'm going to try to investigate several generators and how they respond to a dimmer which is driving a 500 watt incandescent lamp. Today we're going to be doing our testing using four different generators. We've got a 15,000 watt Generac here, and then we have a Westinghouse GE 3600 watt generator. We have a Honda EU1000i inverter generator, and a small Sportsman EU1000. Now the Sportsman is a brushless type unit. The Honda is a inverter type, and the Westinghouse and the Generac both have automatic voltage regulator type excitation. The load for our generators is one of these shop lights. These are 250 or 500 watt quartz lamps, and that is plugged into a temporarily wired receptacle here with a 600 watt dimmer, and the dimmer just plugs into a power cord coming from my generator. And then you see my leads lying here for my oscilloscope, and I'm using today I'm using 100x oscilloscope leads. Now what you see in the upper or yellow trace is the power coming from my receptacle to the dimmer module. So this is the output power, and below you see the waveform going into a 500 watt incandescent lamp. Now each time this switches on, for instance here, you do get a slight deviation, a slight distortion in the waveform, but this may be the result of the resistance in the power cord. There's about 100 foot of number 12 power cord being used in this, and so it has some resistance, but the sine wave still is nice and smooth with a very small divot at each time this switches on. I'll reach over and change the brightness of the lamp. Now I'm turning the brightness up, and as you can see, switchover point for some reason doesn't go completely on. It does switch off here, but a good part of the cycle is on. So now I bring this dimmer lower and lower and lower and lower and lower, and you can see the waveform for the going into the lamp changing. Okay, now I'm going to shut the camera down for a minute or two and bring the power on using the generator. Now I've got my Westinghouse 3.6 kW generator supplying the power. Again, the waveform, of course, is not quite so smooth since it's coming off of my generator, and the upper one, the yellow one, it represents the output to the dimmer, and then the voltage to the 500 watt lamp. The waveform is the lower blue trace. Okay, now I'm bringing on the load, and you can see some definite issues here. This kind of bouncing around here. I believe if this doesn't settle down here, I believe I will lock the image. Okay, I've locked the image just to keep it from bouncing around. It's having a little trouble locking in, as sweep is a little off. But as you see, the driving waveform has a significant deviation in it. And this is only a 500 watt load. So the driving waveform, you know, I don't worry too much about the waveform going to the lamp, but any other device connected to this generator in parallel with this 500 watt incandescent load on a dimmer is going to experience this deviation in the waveform. Again, I'll turn the scope back on just for a moment, and as I change brightness to full brightness, down and down and down, and unfortunately it is bouncing around a little bit, but whoa, lost my incandescent light for just a second there. I guess I better shut this down. I'm running a 500 watt lamp on a 600 watt dimmer, so I'm pushing it pretty hard. Okay, lamp is off. Now we'll do a shutdown. Okay, now let's see how these various power sources respond when connected to a 500 watt lamp with a dimmer on it. And the first power source is my receptacle there in the shop, and the yellow line again is the incoming power supply, and the blue line is the voltage going to the lamp. And as you can see, the voltage is off, it's off, and then suddenly it fires just a little past the top of the voltage waveform. And I'm going to try to leave that dimmer set at that point through all the various examples I'm going to tinker with today. And as you can see, there is a little swiggle in the voltage waveform. Could be as much as 4 or 5 volts each. This is set up so that right now each division is 50 volts. Each major division is 50 volts. And on the horizontal graph, there are 2 milliseconds per division. So we know that for 60 cycle power, it should be about 16.7 milliseconds to complete a complete cycle. So in fact, I've got a little chart here that I have made up, a little tape, if you will. And as you can see, if this is the start of a cycle, this is the end of the cycle, that's 17 milliseconds, so that's 2, 4, 6, about 16.7, so it looks like the scope is just about right on as far as the sweep speed. Now let's change to our first generator, and that'll be the Westinghouse. And this is the unloaded Westinghouse waveform, and you can really, the supply voltage waveform and the output voltage waveform are one above the other. It appears that there's a little leakage through the switching device in the dimmer, so the output voltage is almost identical to the input voltage. So now the dimmer the lamp has been switched on, and again we're switching a little past the peak of the waveform, and we see the blue line coming across here indicating the voltage to the lamp, and suddenly it switches on here, and when it does, there's a significant voltage drop in the driving waveform, entirely different than when it was being driven by the receptacle. So I thought, let's move on and let's try a much heavier generator. This is the Generac 1500 kW generator. And when I look at that, again the blue waveform is the output to the lamp, and the yellow represents the voltage source. And again the output, the blue waveform, almost lays entirely on top of the supply voltage source. When the lamp is switched on, this is the waveform I get. I was very, very much surprised that the drop in the waveform caused by the switching of the lamp on is as great as it is. So let's move on and take a look now at the Honda. And the Honda, of course, is the unit that has the inverter output. And the inverter output Honda is seen here unloaded. Again, the waveform, the blue output waveform of the dimmer is following very closely the yellow input waveform of the, and I've got this in here upside down, so sorry about that. When we switch the light on, this is what we see. So I was pleasantly surprised. I thought, wow, the voltage, there is certainly definitely a voltage dip each time the lamp fires, here and here and here, but it's not as great as I was seeing in the other two generators, the Westinghouse and the Generac. They were having a much greater voltage dip as the lamp fired. I was kind of impressed with this little Honda 1000. Actually it's what the 1000 is the peak rating. I believe its continuous rating is listed as 980 watts. And finally, we'll take a look at the waveform as found when we hook the Sportsman up. And we see here again the blue output of the dimmer versus the yellow input. They're almost lying on top of each, the two curves are lying almost on top of each other. We see the characteristic of a brushless type alternator with this voltage dip here and here and here, which is seems to be the characteristic of all brushless type alternators. And finally, when we switch the lamp on, well, things really kind of go nuts. Our waveform, let's say our cycles, if I start here, we see this is the characteristic dip, which for some reason has been made much deeper than the unloaded situation. And then when the lamp fires right past the peak voltage of the supply, then the dip here is really excessive. And I guess the thing to realize is that any relationship to a sinusoidal waveform here is purely an accident. I mean, this really got chopped up with, it just really does not like the incandescent load that's being fed through a dimmer. And from here to here would represent a transient. I guess the power underneath this curve, this voltage curve, from here to here would represent a much higher frequency voltage change, and any capacitive device would tend to draw an excessive amount of current because of the higher frequency. Of course, now this again only applies, well, this dip applies twice in a cycle, although this unexpected increased dip here is also very significant. So this represents, if you had a harmonic analyzer, which I don't have, it would represent a really high quantity of transients. And just as a summary here, I'll set this under here. I measured the voltage dip basically on the leading edge of the curve, and my little Westinghouse 36 dropped to 110 volts. My Generac 15 kW dropped about 95 volts. And again, I'm talking about this little divot that happens when the dimmer fires. And remarkably, the little Honda 980 only dipped 55 volts by comparison, and the Sportsman dropped 150 volts, much higher than what I really expected. But in addition, we know that the excitation technique, the brushless excitation technique, it seems to be much less stable, and this dimmer load really messes up the waveform on the Sportsman. Back in about 1987, Honda came out with the first inverter generators, and it offered them some features that previous generators really couldn't compete with. For one thing, they were no longer limited to the 3600 RPMs, and they could, if they desired, speed the engine above 3600 in order to get more horsepower out of a smaller engine. So lightweight, and also the waveform was produced electronically, which got them away from being tied to the architecture of the inverter producing the waveform. But it's obvious from what we have seen here that when the inverter is driving a really nasty load, a dimmer into a quartz bulb, we did get significant distortion. And if we had a number of lamps and dimmers, let's say in a house or something that you were feeding with this, you could see that probably this waveform could be really pretty badly chopped up. So it's not exactly guaranteed to give you a distortion-free waveform. But now, having thrown a few stones at at Honda and their beautiful waveform. I must say that of the 4 generators that I've worked with, Honda has handled the problem with the distortion much better than the other 3 generators. So, and this is the smallest and lightest of all the generators that I was tinkering with. For example, when we saw the dimmer fire, was about a 55 volt drop in the output, the little divot in the waveform. However, the other generators, the divot went all the way from 95 to 150 volts. So my hat is off to the technology that Honda has come up with in this inverter. However, we've got to remember that if the load is nasty enough, a switching load, it's possible that you can get quite a bit of distortion even in an inverter generator. And if you have other sensitive electronics hooked up to the circuit that's driving these nasty loads, they're going to be exposed to this distortion. Well, thanks for watching. Hope this gave you something to think about.